Hi everyone, welcome to today's live stream. So I'm Jerome Petezzoni, and today we're going to talk about Kubernetes during rush hour. I am super happy that we have folks hailing from many different places, US, Canada, Dominican Republic, Europe with Spain, Perpignan, which is south of France, Helsinki, Rennes. That's really cool. When we picked that time, we were precisely hoping for this. You know, it's a nice time, both if you're on the West Coast, East Coast, and in Europe and Africa as well. It might be a little bit less friendly for folks in India or Asia, unfortunately. But who knows? Maybe next time we're gonna pick a time that works best for them as well. So it is Kubernetes during rush hour. I'm Jerome Petezzoni. So I used to work at Docker, and if you have heard my name before, it's probably in connection with Docker and some of the talks I did there back then. I spent several years in this startup, and today now I'm a Kubernetes teacher and pirate. Pirate because just last week at KubeCon Europe in Paris, I gave a talk with a friend about database operators, and we were dressed up as pirates. So that was both hopefully instructive and also super fun. So if you want to learn more about database operators and Kubernetes and how to run your databases with replication, backups, failover, etc., don't hesitate to check out that talk. When I'm not hacking on containers and Kubernetes and all that stuff, I like to play music and tinker a bit. And if that's also one of your interests, you can check that link there. Speaking of links, so you probably noticed there is a QR code on these slides. You can scan that code to get the slides. If I had been a little bit more smart, maybe I would have copy-pasted the link in the chat as well for convenience, but we're going to put it in the show notes, as they say in podcasts after the live. And each time there is a pink thing in the slides, that's a link to more information. Yay! So today we are going to talk about stuff like pod disruption budget and resource pressure, preemption, nominated node, out of memory killer, etc., etc. All these concepts, you know, if we are playing one of these party games where you need to guess what's the common denominator between all these things, all these concepts have to do with what happens if you run a bunch of things on your Kubernetes cluster, as in too many things, and you use a lot of resources, as in too much resources. So basically what happens, you know, does everything blow up? Do some workloads go away while others keep running? That's what we're going to discuss. So first we're going to talk about traffic surges. So what happens, you know, well, first, what's a traffic surge exactly in the context of Kubernetes? We're going to see, so what happens when the cluster is globally very loaded, like when there is a lot going on. We're going to also see what happens on the level of a node. And then we're going to talk about maintenance, like planned maintenance, you know, like, oh, I need to upgrade that machine, like maybe I need to upgrade the kernel or to upgrade the version of kubelet, or, you know, there was maybe another, like yet another CVE, like a security vulnerability, and I need to do something about it. So that would be a planned maintenance. And we're also gonna talk about unplanned maintenance, which is, you know, it's a kind of a very business, almost bullshit way to say an outage. You know, it's like when you blow up a rocket, you don't say, oh, we messed up and we blew up the rocket. You said, the rocket experienced rapid unplanned disassembly, you know, something like that, which means it blew up. So here we're going to talk about this planned and unplanned maintenance and how do we do that on Kubernetes. So first, traffic surges. So What we're going to do is that I'm going to have a cluster here. I'm going to log into that cluster, and I'm going to take a minute to give you a tour of the Kubernetes cluster, and we're going to scale up a workload on that cluster. Just a little heads up, I'm going to work with a cluster that doesn't have auto-scaling, but pretty much everything that I will talk about also applies for scenarios with auto-scaling. The only reason why I'm not going to use auto-scaling here is just because, for the sake of the demos and timing, when you do auto-scaling, there is a lot of waiting until things actually auto-scale, and I wanted the demos today to be pretty fast-paced and so on and so on. But everything I'm going to show you here would work with auto-scaling and with HPA or KEDA, which is an absolutely awesome auto-scaling framework, or the Prometheus adapter, etc., etc. So I'm not gonna talk about these today, but keep in mind that it's, as we say, orthogonal, it's independent, and we could sprinkle some of these things on the cluster, and everything I'm going to tell you would remain the same. If you have already seen some of my talks, you might know that often I use an app called Color. It's a very simple web app. It just serves like a static page, and it's called Color for a reason that you will see in just a minute. And here I'm going to use BigColor, which is a variant of that app that uses a lot of resources. I mean, 800 megs of RAM, in the grand scheme of things, is it a lot? I don't know. Well, if it's just to display a static web page, yeah, it's a lot. All right, so let's, that's the cluster here. We have 4 magnificent nodes, and they are of modest size. We have, let me zoom that a little bit maybe. Right, we have 2 CPUs, 8 gigs of RAM. So, we're not going to tackle any heavy machine learning workloads with that, but for today's demos, that will be perfectly fine. For convenience, my nodes are called node 1, 2, 3, 4, and node 1 is reserved for the control plane. All right, so let's deploy my BigColor app. So I'm going to create a deployment called Blue with image jpetazo BigColor. Then I'm going to expose deployment Blue, port 80, and let's give ourselves a node port. And now I'm going to curl that. So 30113, and that's why it's called Blue. So like I said, it's giving us a static page, but since I called it Blue, you can see there is a blue dot in the beginning of the line. If I had called it red, there would be a red dot, green, there would be a green dot, and so on and so on. So this is what I use to do literal blue-green deployments, because you can literally switch, from the blue pods to the green pods, and as you do the switch over, you can see the blue dot becoming green, and so that's pretty cool. So anyway, that's today's app. So and this app is using, like I said, a lot of resources. If I do kubectl top pods, you see it's using 800 megs of RAM. Again, yes, that's a lot for a silly app that just gives us a static page, but that's for the needs of today's demos. So for instance, I could start by doing a little benchmark on this. So let's see, I'm going to use, first let's make sure I can open many files, and I'm going to use Hey. Hey works like this. You say, for instance, benchmark for 10 seconds with 100 concurrent connections, and benchmark localhost on port 30113. It's going to send 100 connections in parallel. Imagine 100 threads. Well, actually it's Go, so Go routines, sending requests in a loop for 10 seconds. And the result is, on average, it took 0.2 seconds, etc. Okay, so that worked, perfect. I I can see that my pod was using a bunch of CPU. Great. Okay, so now let's scale that up a little bit. All right, so let's have 5 replicas. And you know what? I'm going to keep an eye on the load on the cluster. And this is going to be a very, I would say, very kind of low-tech way of monitoring what's going on. I'm using kubectl top nodes, which relies on the metrics server and gives me an almost live view of resource usage on the cluster. I say almost live because there is a little bit of delay between the moment when the metrics server is collecting that data and the moment when I see them in kubectl top nodes. So yeah, you see I can send a bunch of requests and you can see like the CPU is coming up here. We're also using a little bit of memory, but we still have a lot of breathing space on the cluster. Okay, so far so good. Everything runs smoothly. Awesome. Now, what happens if we scale up a little bit more? Like, let's say I scale up to 50 replicas. And by the way, you know what? I'm going to use K9s for that part. I don't know if folks already know K9s. If you do, great. If you don't, even better, because it means that today you're going to learn about a really cool tool. K9s gives you like this this kind of text mode user interface, and you can do, for instance, okay, let me, for instance, you can do a colon deploy to see deployments, and then I'm going to type S, like scale up to 50 replicas. Yes, now let's go to pods. And okay, so we have plenty of pods coming up and everything seems fine. Oops, now we start having problems. We can see that we have some evicted pods, we have some OOM killed, we have, okay, what's going on? Well, what's going on is that if we do the math, you know, like my app is using 800 megs of RAM per pod. And so I'm trying to have 50 pods. So let's do the math. 800 megs times 50 pods. That's what, 40 gigs or no? Yeah, 40 gigs. That's 40 gigs. And on this cluster, I have 3 worker nodes with 8 gigs each. So yes, we are, I would say, grossly oversubscribing this cluster. And how can I say, like hell is breaking loose at the moment. You can see here the memory percent. Yep, we are like above 100% memory, which is really, really bad. You should never be above 100% memory because that's how you get, not ants, but yeah, warning memory level. You get all kinds of interesting issues when you do that. Okay, so we are going to scale back a little bit, go back to deployments. You can see, yeah, we only have like 25, 26 pods being ready at any given time. Okay, let's scale back down to 5. Okay. And so we already brought up some of the keywords that I promised you that we would talk about today. You know, eviction, OOM kill. So we're going to talk about eviction in a few minutes, a little bit later. Now, the OOM kill, I'm sure that many of you have already seen that before, but just in case, on a Linux system, the way it works is that the kernel is constantly trying to make sure that you have some memory available. It's a little bit, you know, like imagine you're at home and you're trying to make sure you always have a little bit of cash by the door, so when you have, you know, the delivery or something like that coming, you can give a tip to the delivery person. And so the kernel is like always constantly like making sure we have a little bit of spare cache, I mean a little bit of spare memory. And so when you're running low on memory, it's going to try, I would say, more aggressively to recover memory. And at some point, if it really can't, if it's like, well, I tried everything, all the unused buffers and caches and everything, but we're really out of memory, the only way it can recover memory is by killing processes. And so it's going to select one process using a very advanced heuristics. It's not exactly the process using the most memory, but it's kind of like that, and it's going to kill that process, which is going to free up all the memory that was allocated by that process, and hopefully that will be good enough to continue operations. It's a little bit like if I go back to my cache jar metaphor, you always want to have a little bit of cache in the jar, and if you're running really, really low, at some point you're going to just take like whatever you have in the house and sell it to have cache. So if you sell some old junk that you don't need anymore, that's great, but if you sell the couch and the TV, that's going to maybe be inconvenient next time you want to watch your favorite TV show. So same thing here, we have a bunch of pods that have been OM killed because we were out of memory. Okay, so meanwhile, memory usage went back down, good. So now at this point, we could think, wait a minute, is this really supposed to be that way? Are we really supposed to run our workloads and have them being killed when we run out of memory? That doesn't seem right. And yeah, that's not right. That's not how we should do it. We should allocate, we should specify resource information so that's what happening, right? We scaled up, and so cluster goes brr. And that didn't work, okay? And so the problem is that, I'm trying to make a little pun here. We're making a lot of requests, but we haven't set requests. Like, what? We're missing this. Okay, this is kind of the path inside a deployment manifest to the thing that we're missing. So in the pod spec, we have a list of containers, and these containers should have resources requests. So basically, normally when you run stuff in production on Kubernetes, for each container, you should indicate how much memory and how much CPU you want to request, kind of to reserve for that container. It's a little bit like when you want to run something in the cloud. When you create a VM, you have to indicate the size of the VM. So same idea here. If you don't indicate a size, if you don't put the resource request, you live in this wonderful fiction where memory and CPU are infinite and resource usage of your programs is 0, and you never run out of RAM and everything. Now we know this is a fiction. We know that in the real world, our code needs CPU cycles and RAM, and so we need to tell Kubernetes how much we need. All right, so that's what we're going to do. So I come back here, and I'm going to kubectl set resources deployment blue, and I'm gonna put a request for memory like 1 gig and CPU 0.25, like 25%, aka 1/4 of a core. So when I do that, this is going, so just to show you what exactly that did, it added that little block here in the deployment manifest. That's what it did. So if you're deploying with YAML, you can just edit the YAML to put that, but here I just wanted to be, I don't know if it's fancy or lazy or what, but I wanted to do that from the CLI. You can also totally do that. Now, if I look at my pods, I have like a bajillion pod in an error state here. I'm going to talk again about these in a few minutes, but for now, just to help us see what's going on a little bit better, I'm going to get rid of these pods and I'm going to delete the replica set that created them. So it's going to be that one. There we go. And so now if I go back to K9S, there we go. It's all nice and clean, and all the pods in error state are gone. Perfect, I like it. So there we go. We have our 5 blue pods, and this time This time they have resource requests. So this time everything should be fine. Like if I go back to deployment and I scale to 50 pods and I go back to my pods. Okay, so it's a little bit better in the sense that we don't have big scary red pods, which clearly mean error. Well, that's kind of interesting actually. In China and some Asian cultures, red is actually synonymous with luck. So in the West, red is like bad, you know, red it's like, oh, stop, danger, etc. But it's not a universal thing. Anyway, but at least we don't have pods being evicted or OM killed, etc., etc. But we have a bunch of pods that are yellow, like pending. So what is that about? What's going on when we have pending pod? The idea is that when you put resource requests, this is a reservation. You're like, hey, I need 1 gig of RAM for that pod. So either you can guarantee that you have 1 gig of RAM for the pod, or don't bother, don't run the pod. And in that case, the pod remains pending. And if we take a look, you know, if I get pods and I, you know, like if you want to see what's going on a resource on Kubernetes, often, you know, the first thing we think of is, hey, let's check the logs. But I think even before that, there is using kubectl describe. So here, you know, like if I try to look at the logs of that pod over here, kubectl logs, it's like, nope, nothing. But I can do describe pod. And in the messages, we're going to have something really insightful. It says failed scheduling, 0 node available, insufficient CPU, insufficient memory, no preemption victim, etc., etc. So that means the cluster is kind of full. You know, we can't fit more blue pods right now. Now, the nice thing is that at this point, I mean, okay, we only have, how many do we have actually? We only have 21 pods up and running, but now they are running, I would say, in a more sustainable and healthy way. They don't get like killed and everything. So that's kind of a little bit better. By the way, here, if we had cluster auto-scaling, that's where it would kick in when you have pending pods. Simplifying a bit, but when you have pending pods, the cluster autoscaler is like, if only we had a few extra nodes, we could accommodate these pods. So you know what? I'm going to provision new nodes. All right. So, however, we could, you know, when we say the cluster is full, this is kind of subjective. Like, let's see what happens if I create now some red pods, create deployment, red image, jpetazzo, big color, and then to our greatest surprise or not, but the red pod is running. So why did Kubernetes start the red pod and not the blue pods? That's because the red pod didn't specify a resource request and limits, so it's living once again in this fiction that it doesn't need any memory, any CPU whatsoever, and then Kubernetes is happy to actually start and run it. Now, there's a pretty good chance that eventually that, you know, if I have more of these pods, I'm going to drive that the resource usage. Ooh, there we go. Like, you know what? I think if we wait a little bit more, something's gonna give here. You know, but I'm not gonna go there right away because it's the topic of the next part. What I want to do is, though, I want to say, hey, what if I have a workload that is more important, and so I really want my more important workload to run, even if it's at the expense of the other one. Like, for instance, okay, first, let's actually set resource requests on the red deployment. That resource deployment red, okay, great. And then let's try to scale deployment red replicas 5, and let's see what happens. All right, so we have a few pods that are being created, others that are pending. So these ones don't have resource requests, so that's why Kubernetes is like, sure, I'm gonna start them anyway. Prediction, if we were to wait a little bit, eventually these pods would just blow up because of resource exhaustion, but the other ones are pending. Okay, how can I tell Kubernetes these are important pods, so please start them even if it means shutting down the other pods? We do that with priority classes. So priority classes, I'm going to create a new priority class, and then I'm going to assign it to that red deployment. And we do it like this. Create priority class, let's say red, dash what? Whoops, dash help, dash value, and I'm going to put 9001 just so that it's above 9000. It doesn't need to be above 9000, it just needs to be above 0. And now I'm going to assign that priority class to the red deployment. All right, so edit deployment red. And in the pod spec, which is here, I'm going to put priority class name red. And before committing that, let's see, I'm going to do a kubectl get pods -o wide --watch. Okay, there we go. Maybe -- output watch events. Yep, that's great. Let's unzoom that a little bit, but also zoom it so that you can see it a little bit better. Yep, there we go. All right, and let's go, let's do it. So we can see that a lot is going on here. We can see a bunch of pods being terminated. So the thing that's really interesting is you can see, let's scroll back. Yeah, we have this nominated node column here. What is it for? This is a kind of little placeholder that the scheduler is going to use to keep track of where that pod should go in the context of preemption. So what happens is that, conceptually, 30,000 feet overview, we have red pods coming in with a higher priority, and the scheduler is going to be like, okay, I can evict, I can remove some blue pods to make some space for the red pods because they have a higher priority. So what it's going to do, it's like, yeah, here, if I remove the blue pod on node 2, then it makes some space. That's what you see here. Actually, this is node 4. See that little block here? We can see, so basically it's creating 3 red pods. Then it's like, okay, we're going to terminate blue pods to make some space, and we're going to note on the red pod, it's like, hey, I can't really put you on node 4 yet, but I'm kind of pre-booking you on node 4. That's the nominated node idea. So I'm kind of pre-booking you on node 4, and a little bit later, so LPJHK, where is that one later down? There we go. And a little bit later, you can see here we have a bunch of blue pods being terminated and deleted, so making space. And at that point, the red pods can actually go on their destination node. So that's what this nominated node thing is for. And so now if we take a look at our deployments, you can see that prior we had 20 something blue pods. Now we're down to 16, but we have 5 red pods that took over. And so what's pretty interesting is that, as you perhaps may guess, now if I scale down deployment red, what do you think is going to happen to blue? Is it going to scale up, scale down, remain the same? well, it should scale up because we're making space. There we go. As I remove the blue pods, sorry, as I remove the red pods, the blue pods that were pending, you know, waiting for capacity, they can step in. So this is the kind of stuff that's pretty convenient if you are running on the same cluster, you know, maybe prod and pre-prod, and that way you can have prod with a higher priority. Or maybe you have some, you know, background workers like processing messages from queues or whatever, and you can have these have a lower priority so that if you have some higher priority stuff coming in, you can deprioritize the stuff that can wait, basically. So that's a nice way to make efficient use of the resources that you have at your disposal. Okay, pretty cool. All right, so now what happens when we have an overloaded node? And so we're going to do that. Once again, let's create deployment green, still with jpetazzo big color. And let's give me like 10 replicas right away. And let's see what happens with that. Okay, the replicas come in, great. They come in, but you can see there is some stuff going on here. If I go back to my K9S, what do we have here? All right, we have eviction coming in, just like in the beginning of the stream. So what exactly is going on here? What's happening is that the kubelet is assessing that the node is under pressure. And so here I have a mandatory like under pressure anyway. So what exactly happens here? Kubelet is constantly monitoring resource usage on the node, specifically memory and disk usage. And when you hit a given threshold, it's like, hold up, we are under pressure. And at that point, it's going to start the cleanup, if you will. If I go back to my metaphor about, you know, hey, you have a jar with some cash and coins at home, and you always want to have at least, I don't know, $10 there, so that when the delivery person shows up, you can give them a few bucks or even 10 if they did an awesome job. So basically, when you are below $10 or below, let's say, 1 gig of free RAM, then kubelet is suddenly like, hold up, stop everything, we need to free up memory or we need to fill up the tip jar. So that's what's going on here. Now, so some little details here. The default value for that threshold is 100 megs of RAM, and that's really, really low. When you only have 100 megs of RAM available, you're already kind of deep in the red, kind of. What I did on these clusters is that I put that for 1 gig, which is good for the demo, but also good for production workloads, in my humble opinion. All right, so what happens exactly? So kubelet is like, okay, I need to make some space here. It's going to select the pods to evict, and it's going to select the ones that are that are using more than what they requested. So if they request 1 gig, but they use 2 gigs, they go away. If they requested nothing and they use something, even if it's really low, they go away as well. So the idea is that worst case scenario, you know, like if you end up removing everyone who is exceeding their request, who's exceeding their reservation, are we guaranteed to have enough space after that? The answer is yes, because the requests are precisely, they are reservations. You know, like if I have 8 gigs of RAM on the machine and I have pods who need, let's say, 1 gig, I'm going to be able to put 7 pods, not 8, because there is a little bit of like padding for system, etc. So as long as I'm using less than what I reserve, I'll be fine. That's the idea behind that. There is no overcommit on the resource requests. That's the key thing with Kubernetes. And so that's kind of why it's strongly recommended to put requests everywhere, and ideally to make sure that we don't use more than what we requested. If you use more than what you requested, you are, it's called bursting in the Kubernetes vocabulary. And then if the node is under pressure, then the pod might be evicted. Now, when the pod is evicted, another pod is recreated immediately, and so that leads us into, into this scenario where we have a bajillion evicted pods, like many evicted pods. Oh my God, so many evicted pods. So what's going on here? How do we clean that up? Well, at first, you know, I was like, okay, there seems to be a bug here because this is going to go like out of control. We're going to have 1 million evicted pods if I leave this running overnight. No, there is a cap. After 12,500 pods like this, it's going to start cleaning up the old pods. Why this specific value? Well, why not? Basically, they needed to have a value and they were like, let's put 12,500. Now you might wonder, why do we want to keep these pods around in the first place? You know, what's the point of keeping these? Well, because that way you can see what happened to them. You have a trace, you know, you can see, oh, that pod got evicted. You know, instead of the pod like mysteriously disappearing out of the map, no, it gets evicted and you can see what happened. You can probably look at events and the evicted, the node had condition, memory pressure, so we know exactly what's going on. We could look at the logs and that kind of stuff. So you can also delete them manually with a command like this. For instance, this is just an example of using a field selector. So a selector on not exactly an arbitrary field, but on a field that is not a label. Another way is also to delete the corresponding replica set. That's what you saw me do a little bit earlier. Okay, so let's get things kind of a little bit in order. Let's go back to deployments. Let's scale down green to 0. Yep. And let's scale down blue to maybe, I don't know, 15 seems like a good number. All right. Good. By the way, scaling down to 0, I'm sure plenty of you already know that trick, but it's pretty convenient if you want to kind of, let's say, pause a deployment, but you don't want to delete it, you just scale down to 0. The advantage is that if you want to turn it back on later, you just scale back up to whatever you want and you're good. All right, so now let's talk about maintenance, both planned and unplanned. So in theory, whenever you do a maintenance on a Kubernetes node, you should drain the node. So that means basically you know, all the stuff that is running on the node, you move it aside before you do the maintenance. And it works like this. So in practical terms, let's see. Okay, perfect. This is showing me like the current, kind of scaling levels of my deployments. And so I'm going to do a kubectl drain node 2. So when we do that, it's like, hey, I can't actually do that because there are volumes with empty-dir data and also daemon sets. So this is basically kubectl drain being super cautious. It's like, hey, maybe there is some data here. Are you sure you want to move this around? And basically, I'm gonna be, yeah, I should move it. I really need to do that maintenance. Same thing. Like I think personally, by default, it should just be fine with the pods that were created by daemon sets, since they are always going to be there anyway. But again, it's being very, very cautious here. We're like, okay, drain the node. So, all All right. So you can see we have a bunch of pods being evicted and all right. And you can see that during that time, okay, we're down to 14, okay. Yeah, because of course, since I'm draining a node, I have less capacity available. Okay, so you know what? I'm going to scale deployment blue to just like 10 replicas, all right? And I think it's evicting pods that are already in error state, so that's kind of interesting. What's going on with my green pods? 0, 0, 0, okay. Oh, okay, I see. It's evicting the pods that are in container status unknown. So this is kind of like a more transient condition, but anyway, okay, now we're good. So at this point, node 2 should be completely empty except for daemon set pods. And so actually we can go and check that node 2, and yep, we only have these daemon set pods. Awesome. Now, just, let's do it again because it was fun. Let's uncordon. Let's suppose, I do my maintenance on node 2, I upgrade the kernel and patch the vulnerabilities and reboot the node or whatever. When it comes back, I'm going to uncordon the node, which means re-enable it for scheduling. And now let's drain another one and let's see what happens. Okay, so you can see that blue, we went from 10 to 9 to 5 to 6, 7, 8, 9, 10. So if I look at this, I'm like, hold up, this maintenance is being pretty disruptive. Like for a brief period of time, we basically shut down half of the pods of blue. That's not okay. I don't want to lose half of my capacity when I'm doing a node maintenance. So what can we do about that? The answer is a pod disruption budget. The pod disruption budget, at first when you look at it, oh, that's a really fancy name, but it's literally a budget of disruption for the pods. It means this is the budget, the allowance that I give you to disrupt my application. So you can think of it as a contract, an agreement, a handshake between the folks maintaining the cluster, and they're like, hey, I need to do some maintenance on that node here, and the folks managing the apps, they're like, hey, please don't break my stuff, don't delete all my pods, please do that in a very progressive way. Or maybe the other way around, they can be like, you know what, it doesn't matter. Like typically if it's some web backends or API backends, you want to minimize disruption because if you don't have enough capacity, you won't be able to meet your SLOs. Now, if it's some background workers, you can say, I don't care. If you shut them all for like a couple of minutes, that's fine. Nobody will notice, so go for it. So that's the idea of the pod disruption budget. So let's apply a pod disruption budget. Okay, yes, okay, I have my pdb.yaml here. Okay, first, let's pretend I have done my maintenance on node 3. All right, okay, so now this is what a pod disruption budget looks like. I don't say so. Fairly simple. So basically in the pod disruption budget, you're going to have a selector to indicate to which group of pods it applies. And then you can put a max unavailable or a min available, depending on how you want to look at things. And you can put a number of pods or you can put a percentage. Here, just for demo's sake, I've put max unavailable 1. Okay, so let's create that pod disruption budget, and now I'm going to drain node 4, and now you can see that blue goes down to 9, and then it goes back to 10, and then eventually it's going to go down to 9 again. But normally that my pod disruption budget should be honored, it should be respected, and we should never go below 9. Okay, this is going to take a minute while it's evicting all the green pods in an error state. And yeah, I'm fairly confident that this will, yeah, there we go, that message right there, that's the really interesting one. It say, hey, I cannot evict that blue pod because it would violate the disruption budget. It would not fit the contract, the agreement that we have. So that means it's going to wait a little bit before trying again. And that's it. We did our node maintenance. Now I can uncordon node 4 to re-enable it. Perfect. Okay, so now this is only for voluntary disruptions. Okay, what that means is that if you do a rolling update, like something like kubectl rollout restart deployment blue, you can see, oops, we went down to 8 here. So what's going on? Like why did we not respect the pod disruption budget? Well, because a rolling update is not a disruption. It's a rolling update. So there are different parameters. And if we wanted, we could, patch the strategy for the deployment rolling update to indicate max unavailable 1 there as well. What about, the node pressure evictions when you have a node that is at capacity? Well, that will also not respect the pod disruption budget because it's an involuntary disruption. The node being out of memory, it's not something that Kubernetes can do anything about. It also doesn't work for node outages. If I do an unplanned maintenance, so, like I said in the beginning of the stream, unplanned maintenance is the kind of business compliant way of saying the node crashed horribly. So if you, well, let's see what happens, for instance, when we do that. Let's go on node 3, and I'm going to sudo kill all -stop kubelet. It's a it's a way to simulate an outage. Like kubelet is now frozen, and so it's going to stop giving updates to the control plane. And we're going to see that if we look in the namespace kubectl. There is that namespace, and maybe some of you wondered sometimes what is in that namespace. Well, we have a bunch of leases, and there we go. These leases are basically renewed by kubelet. Kubelet is kind of sending an update every, I think, 30 seconds or so to tell the control plane, hey, I'm still here, I'm still alive, everything is fine. Now, since I stopped that kubelet, like one of these, you can see that the timestamps here, that ones are at like 48, almost 49. That one, see how that one is kind of lagging behind? And if I kubectl get nodes, we can see that node 3 is now not ready. And we can see that, where is my, yeah, you can see that here, blue went down, from 10, we went to 9, 8, 7. We lost 3 blue pods because they are on that node, which is not responding anymore. So this is an involuntary disruption. Okay, keep in mind I freeze the kubelet, I froze, sorry, the kubelet, but that's the equivalent of simulating low-key an outage on that node. I could have been a little bit more hardcore and like shut down the node, or like do something really horrible to the kernel to crash it, but I didn't want to like, how do you say, mishandle any node today. All right, let's resume kubelet. And normally within seconds, we should see these counters. Yep, there we go. These counters go back up because the node is now reporting again. And so the pods that are on the node are now available again, and they are ready again, and this comes back. Okay, so how do we avoid that? You know, how do I avoid... Well, the PDBs can't really help us because, again, the PDB is a contract between you know, me deploying my apps and the folks over there managing my cluster. If I want a contract so that my nodes don't go down, I guess I need to do another kind of contract, you know, pact with the devil kind of thing to make sure like, oh, I want my nodes to never fail. Like, no, that's not really possible. I mean, you can hire consultants and folks to babysit your machines to make sure they're all like fine and healthy, but you can't have 100% certainty that they will never go down. So the solution here is, well, spread the workloads so that when one node goes down, you don't lose all the pods for a specific workload. All right, to wrap things up, you know, like the kind of the take-home action items, whatever. At first, we talked about requests. Well, I didn't really talk much about limits, but the most important part was request. We saw that it was very important to set requests on the workloads that we deploy on Kubernetes. Very, very, very important. Otherwise, when you start being at capacity, kubelet is going to, you know, evict pods and make them throw away, etc. And the pods that don't have request will be the first ones to go away. So you can do that manually, you know, on each deployment, each YAML, each etc. Or there are also stuff like limit ranges. I'm not going to show you that because I want to save a little bit of time for questions at the end, but a limit range is a way to set a default request and or limit in a namespace. So you could, you know, you're deploying your application in a namespace and you're like, I have 20 deployments and I really don't want to be bothered with manually setting all the resources, etc. You can put a limit range in that namespace, and from now on, every pod created will get the default values from the limit range. So that's pretty cool. Then we saw that basically, well, if you don't want to go completely out of capacity, you need to size your clusters appropriately. You know, here basically, how do I fit 50 blue pods that each require 1 gig of RAM? So, okay, that's 50 gigs total. How do I fit that on a cluster that only has 24 gigs of RAM? The answer is, I don't, you can't, it's impossible. So the answer is, well, either you scale up the cluster, you know, you put more nodes or bigger nodes, or you scale down the application, you know, you put less pods, or you optimize the code, or I don't know, you figure it out. Then we also saw that node maintenances are a thing. We rarely talk about them when we do, you know, like Kubernetes 101s or demos, etc., because this is really day 2 or even, I would say, day 3 operations, you know. So we rarely talk about node maintenance, but it's a thing, it exists. And one way to make sure that node maintenances don't completely mess up our applications is to set pod distribution budgets and maybe priority classes as well, so that if things are getting a little bit tight on the cluster, then Kubernetes will be able to know which workloads are important and which workloads are, well, less important. And finally, to protect ourselves against unplanned maintenance, like node crashing down, we need to make sure we have enough replicas and perhaps use pod anti-affinity. Again, I'm not gonna show you that, but the idea is that you can tell Kubernetes, or more precisely, you can tell the scheduler, hey, you see these pods here? I want you to put them in different nodes or different AZs if you're in the cloud, or different data centers if you are on-prem, or different hypervisors, like stuff like that. You can also do the other way around, by the way. If you have pods that are going to talk together a lot, maybe like, you know, the database and some ETL job that accesses that database, and you're like, whoa, latency is really killing me, then you can ask Kubernetes to put them on the same node or the same rack or the same AZ or the same whatever, so that they are closer in the network. All right, so that's what I wanted to show you today. Usually I try to be fairly quick in these, so feel free, of course, to rewatch the replay to check the stuff that felt a little bit too fast. feel free to send all your questions now. I'll be happy to answer as many of them as I can. We are not limited to just 5 minutes of Q&A. I wanted to fit the main presentation in 1 hour, but for the Q&A we can absolutely go over a little bit. Before I start answering questions, I should absolutely say that we at Ardan Labs can help you with Kubernetes stuff, but also Go, Rust, Terraform. We do training, and specifically, if you get Kubernetes training from Ardan Labs, it's probably me who's going to deliver that training. So if you like my teaching style and want to learn about Kubernetes, call us up. But we're also doing other things like staff augmentation, consulting, etc. And we're also hiring. So if you are an expert in these fields and want to join us, you'll be very welcome. Okay, so questions. First, how do we help engineers to right-size requests and limits? That's an amazing question, and I'm going to try to give you a little sense of how we could do that. So first, if we use kubectl top pods, we're going to see the resource usage of these workloads there. So you can see here, okay, 780 megs of RAM, no CPU usage, okay. I have some other more interesting clusters where there is actually, fluctuating memory and CPU usage. So I would say this is kind of level 0. If I don't have Prometheus, I don't have CloudWatch, I don't have Datadog, I don't have all these things, but I can at least have that to take a look at the instant resource usage. Now, it's even better to look at historical data. So here, if you want to go open source all the way, you could install Prometheus. And personally, I have a tendency to install Prometheus stack because it's really easy to install. It's literally like one Helm chart, and it's giving you Prometheus plus a bunch of exporters plus Grafana, and that gives you like a really good starting point to see what's going on the cluster. Of course, there are also many commercial offerings with Datadog and Splunk and New Relic that all have like pros and cons, and that also work really well. So the idea is you look at your graph and you're like, okay, I see that we need approximately 2.5 gigs, so that's what I'm going to use. Now, there are ways to automate this, and there is Robusta KRR. I absolutely love that one. It's the Kubernetes resource recommender, and it's going to look like this. Let's see if I can put that kind of full screen here for our enjoyment. You can see that it's kind of, so you need Prometheus, if I remember correctly, and basically it's going to plug itself into Prometheus, and for each of your workloads, it's going to look at how much it's been using, recently, and it's going to suggest. So for instance, here it's like, hey, you didn't even bother setting a CPU request for that one, so I suggest you put 5M, so 5 millicore, so 0.5% of CPU. That one you've put 10% CPU, but it looks like it's been using a little bit more, so I suggest that you increase that. That one you might want to reduce it. That one looks pretty good. It's also using colors to indicate if you're close or kind of far off. So this can help a lot. All right. So that's one way, to help to right size. There are other techniques. There is something called the VPA, so the vertical pod autoscaler. And yeah, I saw that some folks mentioned it. So disclaimer, personally, I'm not a huge fan of the VPA, and I'm going to try and explain why in maybe a couple of sentences. The VPA is basically kind of automating what the KRR is doing. So at first you could think, well, automating is good. Well, except if you have a workload with a memory leak, it's going to be impossible to distinguish from a workload that is legit needing more and more memory over time. So that's why I prefer, I feel like we would need a word, but the word I use personally to distinguish from automation is mechanization. I don't know if it's gonna hold or something, but so automation is like, I do nothing and stuff happens. Great. Mechanization is like, I do nothing and I get some recommendations popping up and all I have to do is like push the button, you know, okay. I don't know if you've seen like that Simpson episode where Homer realizes that he can work from home and he has like, you know, this kind of bird thing that does like that automatically, and he realizes that his job can be replaced by that little bird to just click to press OK on his keyboard once in a while. So that's what I call mechanization. You know, you have suggestions and you do OK, OK, OK. But once in a while, you know, the human can kick in and be like, wait a minute. This is supposed to be a load balancer and I see it's been slowly increasing memory usage and that doesn't seem right. So that's where the human in the loop can jump in and adjust things. Of course, it totally depends on your context and so on. You know, like if you're working with thousands of apps, maybe you want to go the fully automated way because it's going to save you a bunch of time and that's going to be great. But if you just have a few apps, then the semi-automated, what I call the mechanized way, might be a better way to go. You know, it all depends. All right. Other question, how does the scheduler know where is the memory limit to schedule workloads on a node? So basically when a node registers itself to the control plane, it's going to be like, hey, I'm node 1 and I have that amount of memory and that many CPUs. And the scheduler is going to use that information. So here, example, we have 2 CPUs. So if I try to put requests, the scheduler is going to make sure that we never exceed, sorry, let me try to rephrase that in a kind of formal way. The scheduler will make sure that the sum of the requests doesn't exceed the allocatable capacity. Or if you want to see it another way, you know, sometimes in venues you have a sign that says, you know, no more than 65 people in that room because of fire code reasons or whatever. So that's the idea here. When you do requests, it's like people going in, and when you hit the limit, then it's like, nope, we can't admit more pods, or rather we can't allow more requests, we can't allow more reservations. So that's how it works. And then you can have a little bit of extra padding. I think I mentioned that, but if you look at this, you're going to see that for the CPU, capacity 2, allocatable 2, so same number. But for memory, you can see that this node has 8 gigs of RAM, but only 7.3 is allocatable. Like basically, there is a little bit of memory that has been set aside for the system and that won't be requestable, so to speak. All right. I hope that answered your question, but if not, don't hesitate to send a follow-up. Next question, do I know an audit tool to check the values on containers of every Kubernetes nodes? Okay, so I have one that I kind of like. It's good for, let's say, modest size clusters, and it's a kubectl plugin called view allocations. And I do view allocations -u. Okay, that's a lot of info, so let's scope that a little bit just to memory, for instance. And as you can see, let me kind of, perfect. So well, we can't really see the first line up there, but that's utilization, that column here, requested, and then the rest, let's say we don't care. Oh, let's see if I can somehow, nope, that didn't work. Let me try something. Okay, go like this, whoops, like this, and All right, and maybe unzoom one notch, and there we go. Okay, so now you can see the labels of the different columns. So this shows me like globally on the cluster, I see, yeah, utilization requested, that's fairly low, but, and you can see node per node. You can see like node 1 really low because that node is dedicated for the control plane. You can see that things are a little bit higher here. So that gives you an idea of where we stand. And you can also kind of slice and dice things a little bit differently, like group by namespace. So that's going to show me my different namespaces. Okay, I only have 2 namespaces with workloads at the moment, so this is kind of not super exciting, but okay. Or just show me nodes, you know, something like that. Or maybe show me by node and by namespace. So really, really super convenient. Of course, as you can imagine, if you have thousands of pods, it gets a little bit less useful. I mean, you need to slice things a little bit less. But I really like this to look at where we are, what's the reservation, and utilization, that's the live usage. So you want these things to be fairly close, and here, yep, we're pretty good. Utilization 33%, requested 38%. That's pretty good. If I had utilization 10%, requested 50%, it's like, well, I requested way too much. So in that case, I would probably want to adjust my requests. So now if I want to do a more systematic audit of all that, I think my answer would go back to the Robusta KRR that I showed you earlier, because it generates this kind of reports. And I haven't used it in a while, but I think you can ask it to sort things in different ways so that you see the most important ones first. Next, what's the difference between requests and limits? Excellent one. So here I only talked about requests. Maybe I just kind of name drop limits a little bit, but basically requests are something for the scheduler. We're kind of telling the scheduler, hey, that pod here needs that much memory and that much CPU, so please reserve CPU and memory for that pod. And that's a guarantee that the resources will be available. Limit, maybe you can guess from the name, but it sets a limit, like a cap on the resource usage. So if you set a cap on memory usage, let's say it's here, so the pod is going to use memory like up, down, and if it hits the limit, it's going to be terminated. It's going to be OOM killed. So the limit is here to make sure that a pod doesn't exceed a certain memory usage. And then for CPU, things are a little bit different. When you set a CPU limit, it's going to act a little bit like, on a car, you can have a speed limiter. So now you can try to step on the gas, but it's going to not go beyond the limit. So that's how it works. If you say, for instance, a CPU limit of 0.8, so 0.8 CPU, that means 80% of a whole core. And so basically it's going to pass some, technically it's going to plug something into the C groups on the machine so that this particular container doesn't get allocated more than 80% CPU time. Whenever it hits that 80% CPU time, then the machine is like, oh, I'm not giving you CPU time anymore until it goes down. I'm simplifying a little bit, but that's the idea. So that sets a limit on CPU usage. And the nice thing is that if you hit the limit, instead of killing the pod, it's just going to throttle that pod. All right. Excellent suggestion. There is also VPA in recommend mode. Thanks Hussein for mentioning that one. I had absolutely forgotten that it was a thing, and I think I should revisit that, because now that you mention it, I vaguely remember. Oh yeah, maybe there is the recommended mode, but I had forgotten. But I think it might also be a good way to have some insights to right size requests. Okay. Oh, so side question, do I set limit on CPUs? There are many arguments about this. So first, just to give a little bit of context, and I suppose since you're asking the question, you know exactly what the argument is about, but for everyone else, the problem when you set a CPU limit is that it can slow down the workload. You know, the example is like, hey, I have an API here, an API backend. It's not very busy, you know, just it gets like a request once in a while, and the request takes 1 second, fine. And so if I look at my Prometheus, Grafana, Datadog, New Relic, etc., I see that it's using like, I don't know, 1 or 2% of CPU. So I'm like, okay, it's using almost nothing. So I'm going to put a CPU limit at 10%. And now when I do that, surprise, now the response time, instead of being 1 second, it's 10 seconds. And I'm like, what? You know, yeah, you just need 1 or 2% CPU, and I put the limit at 10, which seems very generous, and now everything slows down a lot. Why does this happen? It's a little bit like setting a speed limit, but based on a very coarse measurement. Imagine that my favorite example is, imagine that you're making a road trip. I don't know, maybe you're doing the US coast to coast, and my geography is not very good, but let's pretend that it's maybe 3,000-4,000 kilometers. And let's say you're doing you're taking a whole month to do it. So I'm like, okay, we need to, if we run the math, let's see. Where is my terminal? All right, let's take some Python. So let's pretend it's 4,000 kilometers. Okay, so, okay. And Python, I said, Python 3. Okay, distance is 4,000 kilometers. And time is 30 days with 24 hours per day. So the average speed is basically 5 kilometers per hour, right? That's my average speed. But now, as you can imagine, if it takes me 1 month to make that road trip, it's because I stop a lot along the way to marvel at the beautiful scenery and so on and so on. So if I look at this and I want to set the speed limit, imagine I decide to put like a 50 kilometers per hour speed limit, or 30 miles, something like that. Now, my road trip will be much, much, much longer, because the reality is not that I drive 5 kilometers per hour or like 3 miles per hour all the way. It's like I drive maybe, 100 kilometers per hour or 60, 80, 70 miles for a bit, and then I stop, and then I drive again, and then I stop. So that's exactly what happens here. If you set your speed limiter on your car to this very low speed, your road trip is not going to be the same. It's going to be very, very, very long. Same thing with our API request. This is why some folks say don't set CPU limits. My approach is a little bit more in the middle. My suggestion is to, first round up. So, and you have to use a little bit of judgment. But for instance, to give you a concrete example, recently I had to add a bunch of requesting limits on a lot of really, really small services that were really not using a lot of CPU. And so I went with a request of 10% CPU and a limit of 1 whole CPU. So that gives me a good in-between. It's like, well, if you need to, to spike, if you need to burst, you're going to have 1 whole CPU available for you. So yay. But also, if there is a problem, like a memory leak, an exploit, some code that goes on a bunch of Go routines that go away or whatever, then I have the guarantee that this is only going to eat 1 whole CPU and not, the 16 cores available on this machine, something like that. So that's a kind of in-between. Same thing, I had another workload that needed quite a bit of CPU. So, in steady state, it needed like 2 or 3 cores. So we put the request, I think, at 2.5, and the limit, I want to say, at maybe 8 or 16, something like that, because that was a really CPU intensive one, and we knew that it might need to burst. So we gave it a lot of leeway. Some folks also decide, well, no, that's, you know, I just don't want to bother about that. I don't put limits. And I think that's valid too. That's perfectly fine. Do I know some tools to perform Chaos Monkey on Kubernetes? I'm gonna say yes, but not from first-hand experience. Last year at the Kubernetes Community Days Paris, that's the t-shirt I have, it's extremely cool. You see the Eiffel Tower and the croissant, and the little like Arch de Triomphe and so on. But anyway, there was an absolutely awesome presentation by Seeley about chaos engineering on Kubernetes. And there is something called Chaos Cube, if I remember well. Well, she talked about 2 different tools. There was one that was really simple to get started with, like it's like a one Helm chart you install and then it can start to, you know, wrap things up. And there was one that was way more complicated where you can define scenarios and so on and so on. I think the simple one was Chaos Cube and the complex one was maybe Litmus or something like that. The talk was in French, so that's not going to help the English speakers, but I'm sure that if we look at recent KubeCon talks, etc., there's going to be presentations about that. So my approach would be to get started with something fairly simple. I would start with Chaos Cube, and then maybe ramp up to the other one if I want more advanced scenarios, etc. All right. Oh, other question. HPA uses requested CPU, not limited. So if we set a low requested CPU with HPA, it scales up too soon. Yes, absolutely. There would be, you know, that was, so here I kind of deliberately put auto scaling on the side because as you could see in 1 hour, we already had to be pretty quick. But there are some really interesting conversations that we could have around HPA and the trade-offs, you know, basically, do I want things to scale really, really fast, which sometimes is good. Sometimes it's like, oh, I have a peak of traffic. I want to scale up right now. And sometimes you're like, hold up. I want to scale up smoothly because, well, maybe it's a worker getting things from a queue, so I don't want to create, I don't know how to call that, but the equivalent of stop and go traffic, you know, when you're in traffic and suddenly you start to advance and then you have to stop right away and so on and so on. We want to avoid that with our pods as well. So HPA kind of gives us ways to pick the strategy that we want by setting the requests appropriately indeed. All right, I think that's all the questions. Let me double check, triple check, yes. All right, so once again, where is my browser here? Thanks for coming. I suppose like you watching this comfortably from your place or office, etc. But thanks a lot. I hope that was useful. And once again, at Arden Labs, we do a lot of things around staff augmentation, consulting, training. And like I was saying, if you're interested by Kubernetes training, that's probably me that's going to do that. So if you like that teaching style, don't hesitate. We have all kind of Kubernetes courses, you know, from intro, intermediate, advanced, etc., etc. And that said, thanks once again. I wish you an excellent rest of your day. You know, good morning, afternoon, evening, depending on where you are in the world right now. And maybe see you another time. Bye.